All right. So is the screen visible for everyone?
Yes.
All right. So today we'll be starting the next section, which is of matter. And the topic we'll be doing today is ideal gases. All right. So first we'll start with the very basic thing. It's really to measure the amount of how do I measure the amount of matter in a particular substance, right? And you're already familiar with measuring the amount of substances, and how do we do that? Um, we use kilograms, right? So we measure the amount of substances using the units of kilograms. But when we're talking in terms of atoms or molecules and so on, it's better to measure in a different unit, in atoms or molecules. So we define a unit which is known as the mole, or sometimes abbreviated as MOL. Now we use this to measure the amount of matter, which is really the number of particles, right? So mole is used to measure the amount of matter, which also means the number of particles in a body, or really in any substance, number of particles in a substance. So let's start by first defining 1 mole. So a mole is defined, it's given this definition in physics, and then we follow along this definition as the amount of substance that has the same number of particles. So the number of particles are same as as there are number of atoms
Sir, is
in
this
a carbon
similar
atom.
to the ideal gas chapters that we did in AS chemistry?
It's similar. We'll be looking at ideal gases, ideal gas equation. Why is the sometimes when is the ideal gas equation applicable, when it's not? And we'll be talking about the kinetic theory of gases, where we'll be talking about Brownian motion. How do we model a gas? What is a picture that we can use to visualize gases? And we'll talk about many things, right? Temperatures is really another topic in the section of matter. But yeah, so we'll be talking in terms of pressure and the speeds, how our pressure that is exerted on a particle is related to the speed of that particle. That's also something that we'll be looking into, and so on, right? So is that what you were asking? All right. So I think I started off the class just very directly today. Um, I forgot rather to ask if everyone is following along, if the previous chapter that we did, everyone is on board, everything is fine. Uh, the last topic that we did many of the questions as well, from specifically the topic of gravitation. So is everyone following along?
Sir, I
Yes,
do have some
yes.
issues in that chapter, but I'll try to cover up that on the weekend because I was busy on this one.
All right. So by issues, do you mean did you go through the chapter and you have questions, or you still have to go through the chapter?
I went through a little bit of the chapter.
Right. So okay, so the issues that you're talking about are from what you have gone through, and you have some questions from that, or you have some or you still have to go through. Uh, it,
I
all I'm
still
trying to
have to go through a lot, through the majority of the chapter. That's why.
right.
Properly.
So okay. So if you have while you're going through the topics, if you have any questions, feel free to let me know. You can text me on WhatsApp as well. I'll get back to you over there, and then we can discuss those in the class as well, right? If you have any issues whatsoever, so just let me know beforehand so that we can discuss them in the class as well, right? Because I mean, you might have some issues in the topic, and of course when I answer those in the class, it will definitely be benefiting the other students as well, because maybe they might also have that problem. And sometimes it's just so that we don't know that we have the same problem as this person, and then that's beneficial to the entire class, right? So we can do something like that. This is for everyone, by the way.
Sir, I also had one
Yeah.
confusion in one part of that worksheet you sent us. I finished it, but I just had one small problem.
Right.
Can I send it to you
So
on WhatsApp?
yeah. You can share that with me. You can send me a message on WhatsApp. There is an option. You can, I think, you can circle it or something. Or you can just tell me that in this specific part of the problem, I have this problem. Just tell me on WhatsApp or something, and then we can get back to it even in the class, or I'll get back to you on WhatsApp as well. So
Okay.
both things work, right? So it's just that let me know beforehand, before the class starts, so I can do my homework as well, and we can discuss it quickly in the class that way, right? Okay, so this is for everyone, right? So just any question that you have, feel free to text me and communicate those problems with me, and so that we can resolve them together. All right. So okay, so where were we? We were defining mole, right? Yeah. So a mole is really defined as any amount of substance which has the same number of particles as much as there are atoms in the carbon 12 atom, or it's carbon 12. It's also really an isotope. So that's the definition of a mole. Does this make sense to you?
Yes, sir. We have already studied majority of this chapter.
All right, that's amazing. So then we can go through this quickly as well. So now, what type of quantity would this be? A base quantity or a derived quantity? What do you think? Mole. So it's an amount of substance, right? And we discussed that any amount of substances, well, we did not discuss this because it's a topic from AS and this very first topic of physical quantities, but the amount of substance is always a basic quantity, base quantity. So normally it's a mass, right? And which is a base quantity. So in a mole is also the amount, measuring the amount of substance. So it is just a base quantity, and we use MOL to measure this thing. Now we know that the number of atoms, by the way, how many atoms are there in a carbon 12 in a carbon? Let's just write it as C-12 atom of 12 grams. So this 12 grams is just coming from this thing. And how many numbers are there? Anybody?
6.02 into 10 to the power 24.
Very close. 10 to the power 23, right? 6.02 into 10 raised to the power 23 atoms are present. This number has a famous name as well.
Gardner's constant.
Sorry?
Avogadro's constant.
Yes, exactly. It's known as the Avogadro's constant. So we can write this thing as Avogadro's constant, which is 6.02 into 10 raised to power 23. And the unit is inverse of mole, right? So mole minus 1. So this statement, this thing really is telling you that one mole of carbon atom or carbon 12 isotope, it has 6.02 times 23 carbon 12 atoms in it, which has a mass of 12 kilograms. Sorry, 12 grams, right? So does this make sense?
Yes.
Yes.
All right. So it is also in nature, you don't always find all these atoms, or you can say gases really, as single atoms. In nature, single atom gases are not always found, which means because an example is, for example, we have H2, right? Now, hydrogen is not found as a single atom. It's always found as a molecule, right? So two hydrogen atoms together. So any other example that you can think of? Any other example for a gas that is not found as a single atom?
The halogens.
Oxygen.
You mean the halogens? How about oxygen?
Oxygen and nitrogen.
Yeah. So, okay, so you'll have to forgive me because my chemistry is not that strong. I'm a physicist, and I haven't been following along chemistry for a quite long time. So these are halogens, right? Oxygen, are these halogens? They
No,
have
the
7 atoms.
group 7.
Yeah. They're group 7 atoms. Sorry. Yeah. Okay. Perfect. All right. So hydrogen, oxygen, and we have other atoms as well. These exist as diatomic molecules. It's known as diatomic molecules. So it's easier for these atoms to exist as diatomic molecules, and so that's what they do. Now we can move on to the main theme of the topic, which is ideal gas, right? So let's talk about ideal gas and the equation that we can use to represent ideal gases. Now, experiments have been carried out, right, in thermodynamics, which show that if you have a gas which has a mass which is fixed, so mass is fixed, any constant mass, and temperatures are above, so how do I write this? Let me say the mass is fixed and temperature is greater than the temperature at which they can condense, really. So when they're condensing to forming liquids. So temperature at which they condense to become liquids. These are the conditions that, if are satisfied, then there are some relationships that will always hold true. So for example, if I have constant pressure, if the pressure that I apply is not changing. It is a particular fixed value. In that case, the pressure will always vary inversely to the volume, which means that if pressure increases, then the volume will decrease, right? And this also makes sense, right? So if you're applying pressure, you're basically, so for example, if I consider this system, I have a piston, I think it's called a piston, and I push on this, apply pressure, then it will move in this direction. And so the volume, the initial volume has decreased to some final volume, which is smaller than the initial volume. And then if I have, sorry, this was a constant temperature, my mistake. Because at constant pressure, the volume is proportional to the change in temperature. So when I'm applying constant pressure, then the volume would be directly proportional to the temperature. So if I increase the temperature and keeping a constant fixed pressure, then the volume is going to increase. And finally, we have, so we have done constant temperature, pressure, and then the thing is left is constant volume, right? So what would happen at constant volume in terms of what are the other quantities? Pressure and temperature. So if I keep the volume fixed, and let's say that I apply some pressure, and increasing pressure would increase the temperature. Now, these things are experimentally observed. And on the experimentally observed basis, we conclude that we can form an equation out of these relationships. And the equation can be written as PV over T is equal to some constant. Let's call it, okay, let's just write some constant. Now, if I bring this T over there, then I have PV is equal to some constant times the temperature. And this is known as the ideal gas equation. This equation is only true in a case of when the gas is considered to be an ideal gas. It's known as the equation of state, really, for an ideal gas. Equation of state. So what is an
Sir,
ideal
don't we
gas?
have moles in
Yeah.
this equation?
Yeah, exactly. So that's what I'm going to come to now. That's why I didn't box this yet. So this constant is found out to be the number of moles, right? So now most of the thermodynamics is built on experimental evidences, right? There is a whole branch to study thermodynamics in a much more simpler way as well. It's known as statistical mechanics, and it makes called the partition function, and you can extract everything. All the thermodynamics can be extracted from this partition function, but that's not something that you will be going into. Just something that I thought I would say. So this constant is the number of moles, right? And times the constant, which is called a gas constant. Now you can think of it in many ways, right? So this you can say that suppose I'm just talking about one particular mole. In that case, this constant is just the gas constant, or you could just so really what I did was I absorbed the number of moles in this constant. But let's not do that. Let's just say that the constant is this gas constant. Now, this equation that I wrote, all of these relationships, we were talking about one mole. So we picked a mole, that's the most basic form that I can have for the amount of substance at this point. And I checked all of these relationships for that one mole. Now, if I want, for example, I want 2 moles, 3 moles, or an entire gas, then I'll just multiply that a number with this equation, which is n. So this gives me PV is equal to N, the gas constant, and then temperature. So this is for N moles of gas. This is the equation of state. So this equation completely specifies the state of the system, or the state of the gas, and that gas, mind that it is an ideal gas, right? Now this is just a constant. I don't remember the value for this constant. I think it is 8 point something, 8.3 something, right?
8.1.
Yeah, 8.3 joules per Kelvin. Right. So that's the gas constant. And so this is what we have so far. So any problem or any question you have at this point till what we have talked about so far?
So
All right, no question. Okay, so now this equation has some limitations. Now let's discuss those limitations quickly. So limitations of equation of state. Now, because I am a theoretical physicist, and it is this thing among the physics community that we like to think of ourselves above experimental physicists. And so it has been going on for a long time, and it still exists to this day. And the thermodynamics is really based on all the experimental evidences. And so that's why there are bound to be limitations in these equations and so on. Sometimes I like to think that way because, anyways, I'm not promoting that thought. So do not quote me in this statement. Anyways, so the limitations are that, well, first thing is that the equation is going to be not well enough when we have temperatures that are very low. So for temperatures which are extremely less compared to, you could say, at room temperature, right? And the pressure is very high. So very high pressure. In any of these two cases, the equation of state for ideal gas fails. And so of course, we can still overcome this problem, and we can, there are lots of equations that many people have derived, and they have made a table for comparing these values for pressure, volume, and temperatures, right? So they have made a table, and so in that table you can pick a particular value for temperature and compare it to its other properties, internal energies and enthalpy and all of those other properties. But it's not an easy job to do. People have done that, made some tables, and so those tables exist as a reference, and you can, people always look at those tables and work out the values from those tables. Because it's not an easy thing to do. It's done on computers using softwares and then generating the values from the softwares. So anyways, these are the limitations for the equation of state. So it will not be giving you correct answers when the values of temperature are very small compared to the room temperature, right? And the value of pressure would be very high compared to the atmospheric pressure. So that's when the equation of state fails for the ideal gas. Okay, so is that clear for everyone?
Yes.
yes.
All right. Okay, so 1 second. Okay, for some reason, it's not showing me the time for this meeting. Does anyone have it with them, the meeting time remaining, or? Okay, 1 second. Never mind, I cannot see the meeting time remaining. But anyways, okay, so let's see how can I use this equation, use of equation of state. It's a very simple and a very basic example that I'll give you. Suppose that you have 48 milligrams of oxygen, and it is maintained at some temperature 20 degrees Celsius. And suppose the pressure where this 48 milligrams of oxygen is, the pressure is at 1.0, 1.0 times 15, or let's just, 15 is too high, 5 pascals. All right, so that's the situation. Now, of course, you will need something that is known as the relative mass of oxygen, or you can say relative atomic mass for oxygen. So that is given, that is, what is that, by the way? Can anybody tell me from the class? It is the mass number, right? So 16, right? Okay, so now a very important thing that will be talking about when we discuss the topic of temperature, but in thermodynamics, we compute temperature whenever we are using this equation of state or any equations that we'll be using in thermodynamics. They are there when they are going to work as long as the temperature is measured in kelvins. So there is a very easy way to go from degrees centigrade to kelvins, and that is done by, how do you go from degrees centigrade to kelvins? By adding
Plus
273,
273.
right? Yeah, 273. There are some decimal places to this as well, but we'll ignore that. So it's just add 273 to your degrees and you'll go to kelvins. Now, let's try to figure out the volume of this, the volume occupied by this gas. So how would I do that? What's the first thing that I should be doing at this point? Let's write down the equation of state, right? Let's write down the equation of state first of all. And the equation of state says that PV is equal to nRT. Now let's look at this equation. Okay, so, well, I have the pressure, so that's cool. I need to compute the volume, so we'll do that. Gas constant is already known. Temperature is known, but remember to find it in kelvins. And we need number of moles. So that's what we have to do. So what's the first thing that we can do at this point? The very easiest thing to do is write the temperature in kelvins, which would be 20 degrees centigrade plus 273, which would make it 293 kelvins, right?
Sir, we
So
have to
that's,
convert
yeah.
milligram into grams.
You mean mg into grams? Yes.
Okay, sir.
Right. So, and that's what we'll be doing now to find the number of moles, right? So we know that 1 mole of oxygen, 1 mole of oxygen is how many grams? Anyone?
16.
Okay, so but would I be using 16 or should I do something with that value? Okay, remember that oxygen always exists as a diatomic molecule, right?
Yes, I
Yeah. So then 1 mole of oxygen molecule would be 16 times 2. So 2 of these, or 16 plus 16, or 16 times 2, which would be 32 grams, right? So that is something that sometimes people forget, and that's where mistakes can happen. So always remember this thing. You have to remember the nature of the atom or molecules that we're talking about. All right, so now we have to compute the number of moles. First of all, number of moles, or just use n for this thing. Representation of this is n, which is equal to, so how will I compute the number of moles?
It would be 0.048 divided by 16.
Divided by
32 in this case.
32, right? Yeah, so exactly. Great. Okay, so it would be 48 into 10 raised to power minus 3 grams divided by 32 grams. So the units cancel out and you're left with 1.5. What would be, of course, 1.5 times minus 3 per mole. So this means that there are 1.5 times minus 3 per moles. Sorry, why did I put this minus 1? Moles in 48 grams of oxygen molecule. All right, so now we have everything, right? We have P, we have V, sorry, we want to find V. We have N, we have R is just a constant, we always have that, and we have T. So we can use this to find V. So V would be, if I rearrange the above equation as nRT by P, and then now it's just a matter of putting in all the values, right? So you can hopefully do that. And so we'll put number of moles here, R is a constant, value of temperature in kelvins. Remember this. So this is always in kelvins. And then we'll put the value for pressure, which is given to us over here. And so we can compute the volume. All right, so everybody understands what we did over here?
Yes.
All right, so now we can move on to the kinetic theory of gases, and we'll start by, what's the first topic? Let's start with Brownian motion, I think. Let me, all right, so kinetic theory of gas. Okay, so are you all satisfied with the speed of the lectures, or do you think is it too slow?
I'm satisfied.
Sorry?
No, I'm satisfied.
I cannot hear. What, can you please repeat?
I said I'm satisfied.
Oh, okay. So is it okay for everyone else as well? Okay, so I'll assume that it's okay. I'll keep asking this so that, you know, if I'm going too slow, you can let me know, and, you know, we can change the speed accordingly. So, okay, so I'm sure that you all are aware of a Brownian motion at this point, right? So I'll not go into very detail of it. You have studied it in your AS as well, right? So is everyone familiar with the topic of Brownian motion?
Yes, sir.
It's just okay, great. So it's just the really the random movement of particles, right? So for example, in the very beginning, there was this thing that people thought uh, that Brownian motion is really uh, a life nature of particles, or anything that is living thing, right? So in history it was thought as a life nature. So everybody thought that, okay, so they are moving randomly, that is because this it was they first found it from uh, pollen grains, right? And so they thought that they are living, so it's just the live nature of these pollen grains that they're moving randomly. But it took Robert Brown, I think his name was Robert Brown. It took him to realize that he did the same experiment with something else. I don't remember exactly. I think uh, it was sand. I don't remember, but it was sand, and he placed that under a microscope. So place that under a microscope. I'll just draw this thing as a microscope. And so what he found out, that the particles of the sand were also randomly moving, right? So they were just randomly moving here and there, very high speeds. And so when you observe this thing through a microscope, what you see is you'll notice specks of light coming from the microscope, coming from this whatever you place under the observation of the microscope. So you'll see some specks of light. Now, why do you see some specks of light? Because when the light shines or hits those atoms, it will scatter off in different directions, right? So when the light scatters off in different directions, that is observed as these specks of light, and which gives you an evidence that these particles are moving randomly. That's why the light which is scattered, it is scattered in a zigzag direction as well, which proves that these molecules or these atoms that you see, they are moving randomly. And